Hello everyone, and thank you for taking the time to watch our session on resiliency. I'm Chris Coombs, a solutions architect here at Amazon Web Services. And over the next 25 to 30 minutes, we'll explore the many ways we can design resilient systems, how we can mitigate impacts when things go awry, and try to answer the resiliency question of the day, whether to go multi-region or not. But before we get into the details, we need to set the scene and define resiliency. In short, a resilient system is a system that is able to continue to operate despite experiencing a failure and is able to recover quickly. Now, when I think about resiliency, I don't think of it as a checkbox or a test that you can pass or fail. It's a complex characteristic of a system. And as we'll see, it's something we can be constantly striving to improve on over time, but that we must also balance against competing concerns like cost. One way to break down the complex topic of resiliency is to look at it from these four perspectives: disaster recovery, high availability, continuous resilience, and supplier contingency. Some people I talk to think that resiliency is synonymous with disaster recovery, or DR, and that's understandable, as that was all that was on offer for most people pre-cloud. Essentially, DR provides a mechanism to completely restore a system from a last known healthy state, usually in response to an unexpected or catastrophic failure. DR is commonly performed by regularly backing up systems, for example to Amazon S3 or using Amazon EBS snapshots, then restoring the system from those backups. Whereas nowadays we have access to the power and scale of AWS. And AWS has features like AWS autoscaling, which allow us to design our systems to recover from certain types of failure, or even better, to avoid them altogether. For example, using Amazon CloudWatch metrics, we can monitor the CPU consumption of an Amazon EC2 instance, and if we know the application will begin to fail as CPU creeps beyond some limit, say 80%, autoscaling can spin up a new instance behind a load balancer to share the load and avoid an outage. This resiliency pattern is commonly referred to as high availability, or HA. This, of course, begs the question, how do we know our system will respond to failures as we expect? Or maybe even more importantly, how will the system cope with unknown failures? Well, just as with code, testing our resiliency implementation with outage simulations and game days can help us answer these questions. And even better, constantly testing our system by embracing and injecting failures with chaos engineering and tools like the AWS Fault Injector Simulator can give us increased confidence in our implementations of HA and DR. The other lens to look through is supplier contingency. And I typically see this in heavily regulated industries, but dependency management is an important piece of the resiliency story, and this is that taken to the next level. For example, if we're running a health system and access to a third party, which is on our critical path, goes down, what are the next steps? Is there private connectivity like AWS Private Link we could be using instead of the public endpoint? Is there an alternative vendor which provides similar functionality which could be configured as a failover supplier? Or can the system fall back to interacting with the third party by another channel like a call center, and perhaps orchestrate the process with something like AWS step functions? Now, not all customers want or need to think about supplier contingency, but for those that do, this can be a great tabletop exercise to at least identify possible steps that might be taken in the event of a supplier failure. I think it's also important to note that these perspectives are of course not mutually exclusive. For example, to prevent against data corruption or loss, our HA system might also use DR-type backups to enable point-in-time restores. But why should you care about resiliency? The answer, of course, is because it's what end users want. There's now the expectation that everything needs to be available all the time. Resiliency design seeks to unify these conflicting ideas by building robust systems which are resistant to failure. But resiliency isn't the be-all and end-all. As we can see from the well-architected framework, resiliency is just one of the pillars of a well-architected system. And depending on your business, it may or may not be the top priority. For example, your number one goal may be reducing cost. Your own challenges and conflicting demands will largely depend on your business needs, but there are common threads and learnings that we have garnered from the field, and I've organised them here to help us dive deep on this topic. And we're going to take a look at each of these 5 areas: categories of failure, failure mitigations, domain-driven application design, cell-based architectures, and multi-region. First, let's look at the categories of failure. These are really important to help us understand what issues we are designing our system to be resilient against. On this slide, we have a depiction of a relatively simple application, but even in this example, there are usually a number of steps which must complete successfully for each request, and for our end users to have that wonderful experience we're all designing for. Or to say it another way, there are many places where failure may occur, but as long as each of these steps responds correctly, the end user has a positive experience. But as Werner Vogel's reminded us, things do fail all the time. For example, here there's an issue with the client. In this case, the client might have received a bad app update with some incorrect code, or perhaps it's using an expired client certificate. Resolution for client-side issues can potentially be even trickier than server-side faults, as this may require this end user to perform any number of operations to resolve their issue. And whilst we'll touch on metrics later in this talk, one great metric to monitor for client-side faults is support tickets and sentiment. And whilst we don't have time to cover that in this talk, do check out Amazon Connect and Contact Lens for Amazon Connect. Perhaps the most familiar fault scenario is server-side. In this instance, maybe bad code or configuration is pushed to one of the application servers, leading to elevated latencies, error rates, or maybe even a lack of response. Another common failure mode is for dependencies to misbehave. Maybe it's a downstream service maintained by another team that's gone offline, or perhaps it's returning invalid responses. Whatever the issue, if the dependency is on the critical path of the call chain, the effect is the same as if a component we own has malfunctioned. And of course, there's connectivity faults. Whether the failure is in an IP network, load balancers, message queues for asynchronous requests, or the cliched misconfigured DNS, these type of failures can add latency, prevent request delivery, or even trigger a thundering herd of retries. Even an otherwise healthy system might start to become unhealthy under significant load, as the system scale is pushed beyond its previously known maximum scale state. Indeed, we quite often think that horizontal scale provides linear scale, but there are many instances, such as scaling out a database, where additional horizontal nodes may also require additional vertical scaling due to the communication demands between nodes. In essence, we have 4 buckets or categories of failure. In the field, I see a lot of the first, code deployments and configuration gone wrong. But thankfully, due to AWS Certificate Manager, I see fewer and fewer certificate expiry issues, a failure mode which in the past has caused me personally many sleepless nights. And we can reduce the risk of bad code and config with code reviews, unit and integration testing, and I would recommend adding Amazon Code Guru to the mix here, as it could identify issues that humans in the loop might otherwise miss. But regardless of the development mitigations which are available, this does still seem to be the most common cause of failure I see in the field, and so we need some compelling mitigations at the system level, which we'll look at shortly. Infrastructure is a rather broad category, but is mostly commonly evidenced through host failure, or maybe even a rack or network failure. A really tricky failure category is data and state. This could manifest in any number of ways, from local cache drift to complete data loss, or perhaps as a side effect of compute running out of memory or I/O capacity. These causes of failure might not even present themselves during normal operations. For example, this is where those nonlinear scaling problems tend to present themselves. And then there's the high risk but highly unlikely scenarios. This covers a vast spectrum from environmental disasters like large storms to extreme events like meteor strikes. And what makes predicting failures even more complicated is that these categories of failure could occur anywhere in the chain of communication. So there's a sort of matrix here for how you can think about building your mitigation pathways based on location and cause. So let's have a look at some of the common failure mitigation techniques that you could apply. Some mechanisms that we've seen be successful are leveraging redundant components that can provide an alternative path to ensure an operation succeeds if one or more components fail. For example, Amazon EC2 instances behind a load balancer, or a database like Amazon Aurora, configured to run across multiple availability zones. In addition, we can implement retry logic, where clients or components retry the failed operation before hitting a predefined threshold. Retries can be great for resolving transient issues, usually network related, but we must be careful not to create another issue, namely the thundering herd problem. Rerouting in this context is redirecting traffic to a similarly spec'd system, which itself is usually using redundant components and retries. For example, in the event of a bad code deployment, the entire primary system may be unusable, but traffic could still be routed to an identical system with the last version of the code still running. We'll touch on this some more in a moment when we talk about fractional deployments. Rolling back to a known desired state, which could be code or data, works really well in conjunction with techniques like canary or one-box deployments when coupled with automated monitoring. And of course, I'd be remiss if we didn't mention the age-old turn it off and turn it on again. Obviously, this won't do anything in the case of data loss, but for cases like resource contention or stale caches, a restart, whilst drastic, might just help. But there's one crucial piece to failure mitigation that people often overlook, namely considering the reliability design of the technology which is actually performing the recovery. If I had to summarize the approach for designing the recovery system, it would be this: to keep it simple. The recovery system needs to be decoupled and independent from the system it's recovering. It needs to monitor the health of components or stacks and provide safe ways to recover from failure, whether that's triggered automatically or by hand. We've covered failure categories and common failure mitigation options, but what about reducing impact? We refer to this internally as managing blast radius. Essentially, we want to cap the maximum impact caused by an unexpected failure. In order to do this, we need to think of our system not as a large behemoth with seemingly infinite potential points of failure, but to break down our system into easy-to-understand parts for which we can better model failure modes. In practice, many organizations are already undertaking the work to split apart large applications into smaller chunks, for example, in order to improve feature development speed. But we can also add a resiliency lens to that work to see how breaking down large, complex systems can also improve resiliency. But where to begin? Where should we draw the lines between the many parts of an application? With domain-driven design, the model is based on the business context rather than the specific technology implementation. This involves collaboration between both technical and business teams, which is especially useful as the business is likely to understand just how available their particular domain needs to be, which the technical team can in turn translate into resilient architectures. Domain-driven design isn't the only way to achieve loose coupling, but it is one that I see used widely in the field. Coupling is really important from a resiliency standpoint, because if we tightly couple our application and have domains which depend on each other, we decrease the overall resiliency of the system. To combat this, if we break our application into loosely coupled domains with minimal dependencies between them, we greatly increase the resiliency of the system overall. A failure in one domain would not then impact the other domains, thus reducing the blast radius of the failure to a single domain rather than the entire system. Another significant advantage of breaking down a system into independent parts like this is that we can apply different levels of resiliency tiering to each of those parts. For example, the business might stipulate that payment is a Tier 1 service with a high internal SLA, and therefore we can architect the underlying technology to be more highly available, maybe even to use cells. Whereas business reporting, whilst important, may not have the same level of criticality. As such, this could be assigned to a lower resiliency tier. As I mentioned before, the really important part is the collaboration between the business and the technical teams. For example, if we take business reporting, let's assume that the implementation of the reporting engine is licensed per host. In this case, as reporting is in a lower resiliency tier, the technical team could work with the business to establish more conservative recovery time and recovery point objectives, which align more with the DR pattern of backup and restore than an HA-centric design. That being said, if you do have a Tier 1 service and you're looking to supercharge your HA implementation, then cell-based architectures might just be for you. With cellular architectures, we're able to extract amazing value from loosely coupled systems by creating multiple, usually smaller, copies of each domain or service, which we call cells. Essentially, we copy a service into at least 2 cells. We copy everything in the service, from the EC2, the RDS, S3, etc., and we still leverage all of the mitigation techniques we've already discussed, including running multi-AZ HA. But we set a maximum size for the cell so that we can test it to its maximum scale. Scaling out is then done inside the cell to a limit, and then once that limit is reached, new cells are added. In this way, scaling with cells is linear. As each cell is responsible for its own state though, we need a way to make sure that end users who interact with a cell are still able to persist and retrieve their data from the same cell. As a result, we need a routing layer. This routing layer, called the thinnest possible layer or thinnest possible router, is now the only shared component, and to limit blast radius must be kept simple, hence the name thinnest. The router is responsible for routing end users to their allocated cells, whilst it might be tempting to add additional functionality in order to keep the router safe, we still need to keep it simple. The technical implementation might just be DNS. For example, we might spin up a subdomain per customer and route them to the cell using Route 53 record sets. Or for routing on identity information, like that contained within a JOT token, the router might be built with AWS Lambda at Edge or a more traditional reverse proxy. With this method, we need some compute to extract the unique identifier from the JOT, match this with a record in a data store like Amazon DynamoDB, and then route to a cell based on that mapping. But whatever the technology, the goal is to keep this layer as simple and safe as possible. Now, as cells are usually mapped to end users, we can also leverage cells located in different regions to deliver a fantastic low latency experience to users in a cell that's located closest to them. This pattern can also provide additional resiliency benefits too, because, as in our example on screen, cells can be distributed across regions, and if one of the regions becomes unavailable, only end users in the impacted region are affected. The cells, and therefore the end users running in the other region, continue to have service. This cross-region cells implementation doesn't mitigate the cause of failure itself, but does reduce the blast radius of region-wide events. This does also require the thinnest possible router to run across multiple regions, which can be achieved by leveraging a multi-region data store such as Amazon DynamoDB Global Tables. We can also take this one step further and run each of the cells themselves across multiple regions, but that pattern isn't exclusive to cells, and we'll cover that shortly. Now, one of my favorite features of a cell-based architecture is the ability to deploy changes to one cell at a time. Essentially, the idea is to avoid deploying changes to the entire system at once. Rather, changes are deployed to a small subset of components before being rolled out to more and more of the system. Now, quite how fractional deployment is implemented depends on the technology and architecture in use. For example, this concept applies to canaries, blue-green, one-box, and cellular deployments, all with slight nuances. The important thing to note here is that deployment is only one small part of this process. The main benefit is derived from monitoring the deployment against internal and end-user metrics to identify issues before those changes are distributed to the remaining components. This idea of deploying and waiting to gather data we call bake time, and it's an important step in the fractional deployment process. As changes are limited to a subset of components, the blast radius of any failure caused by those changes is significantly reduced. One way to generate signals during bake time is to generate synthetic traffic. This provides outside-in monitoring, often testing interactions between multiple components, just as an end user would. Or to take this a step further, you could implement real user monitoring to gain insight into the end user's experience, which, if we think back to our failure categories matrix, could be experiencing an issue which lies outside of our internal monitoring. So metrics, whether client-side or server-side, provide the bake time data we need to decide whether to continue our deployment or whether to roll back. Now, something I touched on earlier in regards to common failure mitigations was that retries can help with those transient issues, but we need to be mindful that we don't accidentally create a negative feedback loop or a denial of service event against ourselves. For many systems, a cascading failure like this would require a complete shutdown of the system, or maybe even disabling certain functionality to preserve the Tier 1 services. So to avoid shutting down the entire system, one approach to protect against the thundering herd is to apply throttling to incoming requests on any number of dimensions, for example, the header or IP. AWS Web Application Firewall is a great option here. Whilst normally deployed for security purposes, it can also provide the rate limiting required to protect from an unintentional thundering herd. However, it would be better to avoid the thundering herd in the first place, and this is where controlling the retry behavior can be really helpful. For example, where the retry is induced by an internal component, we have more control over the behavior. We can implement exponential backoff with short timeouts and limited retries. And if we enable external access to our system by generating SDKs, we can often set these behaviors as sensible defaults. Again, this is where cells can also provide that additional layer of blast radius protection, because if a particular cell is overloaded, it still shouldn't impact the remaining independent cells, and we can use the techniques I just described to bring that individual cell back into operation. With all this in mind, understanding the categories of failure, how we can mitigate them, how we can reduce the blast radius with domain-driven design and cell-based architectures, the question remains, do we still need to go multi-region or not? To answer this, let's revisit the categories of failure and overlay the likelihood. Most of the more probable causes of failure can be mitigated with resiliency-focused deployment models or by simply taking advantage of AWS's zonal isolation. For example, the EC2 cloud application on screen is deployed across at least 2 availability zones for HA. As availability zones are physically separated by a meaningful distance, they're also independently resilient from unlikely events. In addition, because of the on-demand nature of the cloud, multiple versions of the stack could be spun up to allow for fractional deployments. The zonal model also supports DR, where the system could be recovered from backups into the same or other availability zones. But there may be cases where extreme reliability is required, where either the failure categories, which must be accommodated, include the highly unlikely scenarios, or the mitigations must meet more stringent availability targets. Now, we've already talked about some single region mitigations, such as cellular architectures, which, by reducing the blast radius, greatly increase the reliability of a system, but these can be further improved upon by leveraging multiple AWS regions. Examples of use cases for extreme reliability are where the system supports critical infrastructure, literally where lives are on the line. There are also institutions which, due to their scale and customer base, seek to be always on. In all these cases, multi-region could potentially assist in conjunction with the mitigations we've already discussed. When running these active-active extreme reliability workloads, there is typically a trade-off between availability and consistency of data due to the speed of light between the regions. Now, where strict consistency is not a requirement, multi-region can provide improved levels of reliability by providing additional availability. For example, a system could use an active-passive model to replicate data between the regions and maybe even allow reads from the standby region. Or the other region could even be brought up from backup in the event of a region-wide outage as a DR mechanism. Now, if you are thinking of running with the multi-region failover option rather than active-active, here are a few tips to keep in mind. The first is to use resilient data plane operations to manage failover. For example, we don't want to be executing control plane operations to mutate DNS records, rather leverage Amazon Route 53 health checks, which are data plane operations. Similarly, let's say we would still like to maintain manual control of the failover operation. We could use the Amazon Route 53 application recovery controller, the data plane of which is globally distributed. And it probably goes without saying that those data plane operations should also be executed from the failover region, not the region experiencing issues. Now, as a corollary, whilst I've mentioned multi-region can be a great DR solution, it is important to think about potentially pre-provisioning critical components to remove dependencies on the various control planes. Also, make sure to understand all of the system dependencies. For example, if we wanted to fail over with the Amazon Route 53 application recovery controller, we would want to have backup processes for triggering the failover, for example via the CLI in case of the console itself was impaired. This includes ensuring that there is some kind of break glass IAM user to avoid any dependencies on other identity providers. And of course, test, test, and test. By testing regularly, we can have increased confidence in our resiliency strategy. And as we look forward to the Melbourne region launching in the second half of the year, we can start to think about the additional resiliency we can enjoy when leveraging this second in-country region. If what I've been talking about has been of interest to you and you'd like to learn more, we have some fantastic articles in the Amazon Builders Library, which is a collection of the content describing how Amazon builds and operates software. Some of my favourite reads are about our release process and how to perform fractional deploys on a global scale. There's also white papers and much more content on the AWS website. Or if you'd prefer a more structured learning path, you can take a look at the AWS Skills Builder, our online learning centre. And as you go through the material and build your skills, you might also be interested in preparing for one of our industry-recognised certifications and to join our AWS certified community. So thanks again for sharing your time with me today, and I hope you enjoy the rest of the content at this year's Sydney Summit. And we really value your feedback, so to help us improve our sessions, please share your rating. Thank you.